Hello and welcome back to my channel. Students, as you all know, we are doing problems based on general organic chemistry, and we have already completed the topics like drawing resonating structures, arranging them in stability order, carbocations, carbene ions, aromatic behavior, acidity, basicity. So our motto is to complete all the basic fundamental topics which are included in general organic chemistry, and that is what we are aiming in this problem session. Okay, we will complete all the topics through problems, because you know the problems are the best way to deal with any theory. So let us try to see what is there in problem number 12. So students, as you all can see, you have a compound in front of you on the right hand side of your screen, and you have altogether 7 hydrogens which are marked as A, B, C, D, E, F and G, and you have to think about their acidities individually, and then you have to arrange the hydrogens as per their decreasing strength of acidity. And I have already told you how you are going to decide about the acidity of a particular hydrogen. What you have to do, you simply have to take that hydrogen out as H plus. It will result in a negative charge on the atom from where it was attached, the hydrogen was attached earlier. So an anion will be the result of this removal of hydrogen. It is called as the conjugate base, the anion. Now you will keep on doing this one by one, and as you make that anion the conjugate base, you should check the stability of the conjugate base. You should check whether that carbene ion or anion is stable or unstable. Okay, if it is stable, then you should understand the hydrogen is going to get released as H plus with more tendency. However, if the resultant anion is less stable, so the tendency of the hydrogen to get removed as H plus will be less. So on that ground you are going to put a hierarchy of the acidity. So let us start from the hydrogen number A. This, as you can see, this is our hydrogen number A. We are going to first pull this out as H plus, and a minus charge will come on the carbon from where it was attached, and you can see that this is the carbon which had the hydrogen number A. Now the hydrogen is removed as H plus and a minus charge came on this carbon. Now to assess the stability of this anion, this carbene ion, you have to see if there is any possibility of delocalization of this minus charge, because I have told so many times that the charge, either it be positive charge or minus charge, it is not a good sign, it is not a good thing. So how to make it a relatively better opportunity is to delocalize those charges, and in delocalization of those charges you have to see the possibility of resonance. So as you get this anion, you should see if there is any conjugation which can help in mobilizing this minus charge. So you have seen that there is a minus charge, single bond and double bond. So as you have found a conjugation, so there will be delocalization of minus charge, there will be resonance stabilization of this minus charge, and the stability of anion will increase. So in order to make that resonating structures, as I have already told you how to do that, you have to shift these electrons one position ahead to make a new pi bond, and simultaneously these pi electrons are going to sit over this carbon, and this carbon is going to get a new lone pair along with the minus formal charge. So as you can see, I have drawn the next structure right here. So a new pi bond. As you can see, this carbon has acquired a lone pair and minus charge. Now you have to keep on searching for all those opportunities where this minus charge can be further delocalized, because more it is delocalized through resonance effect, higher will be the stability of this anion and more will be the acidity of the proton which was attached with this carbon. Okay, so once you see this carbene ion, the carbene ion number 2, you find that this minus charge is again in conjugation. How? Minus single double. So as you saw this minus single double, so you found the opportunity. Now you have to make the resonating structure. You have to flow these electrons one position ahead, and the lone pair, they are now going to make a new pi bond, and simultaneously these pi electrons are going to sit over this carbon. So in the next structure, structure number 3, you can see that happening. A pi bond has been created and this carbon has got a lone pair with negative formal charge. Okay, now again all the possibilities you have to see. The moment you were gazing at this carbon, you found that okay, there is one more possibility. How? You can see the minus charge, single bond, double bond. So again there is a possibility of resonance. You have found a conjugation, so you have to make that resonating structure. How to make that? You have to flow these electrons one position ahead like this. Simultaneously the pi bond is going to shift on the oxygen. So as you can see, from here to here a new pi bond has been created. As you can see, a new pi bond has been created, and this old pi bond is now has shifted on the oxygen, and the lone pair will be seen with a negative formal charge. So students, you have seen these 4 structures currently on this in this slide. Okay, now is there any more possibility of resonance associated with this anion? Let us try to find. 4 we have already drawn. Now if you see the carbene ion 2, the anion 2, the resonating structure 2, we have delocalized this negative charge, as you can see. Now there is another possibility as well. You could have delocalized it other way as well. How? Let us try to see in our next slide. So I have again made the resonating structure 2, as you can see on your screen. This was the minus charge I was talking about, and in the previous case from the structure 2 to 3 we went like this, minus single double, and that has already been drawn in the previous slide. Now if you search for another possibility of delocalization, you find that yes, there is another possibility, minus single double. So you could have gone this way also. So now we are going to follow this way. So how to do that? You have to shift these electrons like this, and these pi electrons are going to sit on this carbon, and you will get this resonating structure. So here you can see a pi bond has been created, as you can see, and this carbon has got a lone pair and a minus charge. After you have drawn this structure, you should now see for if there is any other possibility that exists. Yes, there is one more possibility that exists. How? Minus single double. So you will keep on doing the next structure also. So you have to delocalize these electrons like this, and simultaneously these pi electrons are going to sit on oxygen, and you are going to get this particular structure. As you can see, now a new pi bond has been created, and the older pi bond is now seen as a lone pair and minus charge on this oxygen. So altogether, if you count, you will find that you have got 6 resonating structures, because in the previous slide you have already seen you had 4 structures. Now if you find this structure 5 is a new one and this 6 is a new one, so altogether you have got 6 resonating structures. Okay, now This was the story of the B anion. Now let us try A anion. So we have completed the analysis of the anion of A. Okay, now we are going to see the anion of B. So you understand, the hydrogen B was connected with this particular carbon. Okay, so this carbon had the hydrogen which you have removed like H plus, and it leaves a minus charge on this carbon, and as it leaves the minus charge, you should now see the possibility of resonance or delocalization. Then you find that minus single single. From right hand side, no possibility. Now let us see the left hand side. Minus single single. Now again, both the sides you have found that neither side has got conjugation with this negative charge. So very sadly, this minus charge has to remain on this particular carbon, and there is no means it can go from one position to another because there is no conjugation. So there is no conjugation, and you understand, in the case A you got 6 resonating structure. So there was lots of delocalization you have seen. The minus was hopping from one place to another, and it was good for the health of anion, for the stability of anion. And in this case, as the minus charge remains localized on this carbon, is not going to be a good sign for this anion, and it makes it unstable. So now coming on to the hydrogen number C. Now let us try to see the hydrogen number C. Once you see the hydrogen number C, it was connected with this particular carbon. So after removing that hydrogen as H plus, a minus charge and a lone pair comes on this carbon, and now you will search for its stabilization, and the prominent way to stabilize it is resonance. For that you have to see the conjugation, and you have found the conjugation, mind you, how? Minus single double. Okay, so you will float these electrons one position ahead to make a new pi bond, and simultaneously these pi bonds are going to sit on this particular carbon, and this will get a lone pair and a minus charge. So from the structure 1, then I have drawn the structure 2. In this new structure you can see a new pi bond has been developed. The minus charge comes on this carbon with a lone pair. Now again you have to see any possibility. If it is left, then you find that this minus charge is again in conjugation with the pi bond. How? Minus single double. So as you have found the conjugation, you will do the resonance, and as you all know, you have to float these electrons to make a new pi bond, and simultaneously the pi bond is going to shift over the oxygen, and you will get a structure like structure 3. A new pi bond has been developed, and the oxygen has got a minus formal charge along with a new lone pair. Okay, so altogether you have seen now there is no possibility left with this anion. You have seen that it is showing delocalization, resonance, and altogether you have created 3 structures. Okay, and finally in one slide I am going to write all the features of all from A to F, A to G. Okay, I will write whether the resonance was present, how many resonating structures, and etc. Then we'll compare and get a final hierarchy of stability. Now coming on to the hydrogen number D. Now as you see the hydrogen number D, it was connected with this oxygen because you have now to remove the hydrogen associated with the carboxylic group COOH. As it goes away, it leaves a minus charge on this oxygen, and as you see this minus charge, then you have to think about its stability, and the prominent way comes in your mind is the resonance, and you try to find the possibility of resonance, and you get that minus single double. And as you see this, you can delocalize this minus charge one position ahead, and simultaneously this pi bond is going to sit on this oxygen. And as you do that, student, you know a new pi bond, as you can see in the second diagram, and a minus charge on this oxygen. So you get two equivalent structures like structure 1 and structure 2. So you understand the delocalization is present in this case. Two equivalent structures you are getting, and these are not simple structure, these are strong structures. Do you know why these are strong structures? Yes, it is because of the presence of oxygen, because the minus charge is borne by oxygen, and in both the cases the minus charge is held by very strong oxygen, and it can hold the minus charge to a better extent in comparison to had it been carbon. Okay, because oxygen is more capable, more electronegative. So these two are very strong structures, you should understand. Now coming on to our hydrogen number E. Once we see the anion which is formed, as you should know, from this carbon the hydrogen was attached, the hydrogen number E, and it has been removed as H plus, the minus charge comes, and now you should see for a conjugation, and then you find that, oh yeah, there is a conjugation. How? Minus, single, double. So you should delocalize these electrons like this, and these electrons will sit on this particular carbon, brings a lone pair and a minus charge. So from structure 1 you have arrived at structure 2. As you can see, a new pi bond has been created, and this carbon gets a minus charge. Now again you will see that there is again possibility of a resonance. How? Because you have found the conjugation. Minus, this is single, this is double. So how to do that? It will flow like this, and as it flows like this, these pi electrons are going to sit on this particular carbon, and in the next structure you see a new pi bond has been created, and as you see, a new pi bond has been created, and the minus charge and lone pair are sitting on this particular carbon. Then again you find a possibility, and that possibility is, this is a minus charge, single bond, double bond. So you should do that resonance as well. So these electrons are going to float like this, and simultaneously these pi electrons are going to sit on this oxygen, and a new lone pair and a minus charge will appear on that oxygen. Now you have got the structure number 4, and do you see any unusual property associated with this anion? I hope you may have found that property, and it is in front of you. It has got aromatic character, and not just one aromatic ring, it has two aromatic ring, like in this structure. As you can find, first you see this, this is a benzene structure. So as you all understand, benzene structure is aromatic in character. So aromaticity has been created in this anion, and you know the aromaticity gives much benefit. It gives the stability to the anion or any species. So on that ground it becomes stable. Not just one ring in this structure, you can see one more ring present, and that you can realize like this. Once you see the left hand side ring, student, you can believe that, okay, again it's a ring, and this ring, all atoms are sp2 hybridized. It is a flat particle, flat ring, and you understand there is a cyclic conjugation. How? Double, single, double, single, double, and 6 electrons are involved because 3 pi bonds are there in this cycle, and 6 pi electrons are involved from Huckel's rule, 4n plus 2 rule. For n is equal to 1, it gives you answer 6. So not just one, you see the 2 rings which are following the aromatic behavior. So that gives much edge to this particular anion, gives merit to this particular anion. Okay, so I have not drawn all the resonating structures. Why? Because the other structures are also present, but I wanted to emphasize on the fact that it's not a simple anion what it seems like in first go. If you try to make the resonating structures, you immediately find that it is generating aromatic rings, and that is giving the stability to this anion. Okay, so finally we will, once in the final slide when I am doing the comparison, I will again revisit all these things. Now coming on to the hydrogen number F, as you all understand, the hydrogen number F was attached with this carboxylic group, and from here I have removed the hydrogen and it leaves the minus charge on oxygen. And as you understand, once the minus charge comes, you have to think about its stability, and the prominent way to do that is to delocalize it using resonance. So as you see, minus, single, double. So you have to delocalize these electrons like this, and the pi will shift on the oxygen, and once you do that, you get the structure number 2, a new pi bond you have seen, and now the earlier pi bond is now sitting on the oxygen, bringing one new lone pair and a minus formal charge. So the two structures you have seen. If you remember in the in D option also, if you see, you had two structures. Because in D also, in removing the hydrogen number D also, you remove that from carboxylic group, and in present case also you are removing the hydrogen from the carboxylic group. But there is one significant difference between the tendency to give away proton, the H plus, once you compare the D and F. What is the difference? I have taken that in the slide number, this new slide. You understand, if you see the proton which is attached as F, this proton is not a free proton. This hydrogen is basically involved in a very important type of bonding that is called as intramolecular hydrogen bonding. And how it happens, you should understand. This is oxygen, which is an electronegative element, and hydrogen is attached with hydrogen. Once the hydrogen is directly attached with electronegative elements like fluorine, nitrogen, oxygen, then it acquires a strong positive charge because of the electron pull of these strong electronegative elements. And this positive charge meets, whenever it meets nearby some electron cloud, as you can see, this nitrogen has a lone pair which gives the electron accumulation, electron cloud. So this plus charge is attracted by these lone pairs, these electron cloud, and this is called as hydrogen bonding, and it's quite strong in nature, and is happening inside the same molecule, is therefore called as intra. If this is happening between two different molecules, it is called as intermolecular hydrogen bonding. So again I am saying, whenever the hydrogen is attached with the strong electronegative elements like oxygen, like nitrogen, like fluorine, then these strong electronegative elements pull the sigma electrons substantially from the hydrogen because of their power. So hydrogen gets sufficiently large partial positive charge. A positive charge develops on the hydrogen, whose the density of that positive charge is quite high. And if this hydrogen meets an electron cloud nearby, as you can see, this nitrogen provides an electron cloud nearby to this hydrogen, then this hydrogen engages itself with that electron cloud in a strong bonding called as intramolecular hydrogen bonding. And as it is now held by the neighborhood, again I am repeating, as this hydrogen is now held by nitrogen, its neighbor, so it becomes difficult for this hydrogen to be taken away, because not just this oxygen is holding this hydrogen, but this nitrogen in the same molecule is also holding that hydrogen. So it becomes increasingly difficult to give away that hydrogen. So if this type of situation comes, the release of hydrogen as H plus becomes difficult, and it decreases the acidity of that hydrogen. So you saw that in D also you removed the hydrogen from COOH. In F also you are removing the hydrogen from COOH. But in D there was no such type of issue. The hydrogen was not held by intramolecular hydrogen bonding in the case D, but in the case F, the present case, it is held by intramolecular hydrogen bonding. So if it is held, it becomes difficult for this hydrogen to go away from this held position, from this attraction. Okay, so the acidity goes down. So now you are in position to compare in between D and F, because D was a free particle, and therefore it has to be more acidic than this F option. Okay, now coming on to our G, hydrogen. As you understand, this was the carbon from which the hydrogen was attached, and as it got removed, you understand, the minus charge comes on this carbon, and you should realize that this lone pair, 2 sigma bond, this sigma bond, this sigma bond, and this is a lone pair, hybridization becomes sp2. What does it mean? It means that this lone pair is in the same plane of these 2 sigma bond, because sp2 hybridization, all the 3 hybridized orbital are coplanar, they are trigonal planar. So this lone pair is in the same plane as of ring. So this minus charge is now no more in conjugation with this pi system, you understand, because if you do not give it importance, then you may call it as a situation of resonance. How? You will say that minus, single, double. But that is just for the sake of saying. It has no physicality. Physically it will not happen. It will not get delocalized. Why it will not get delocalized? Because these electrons are in the plane of the molecule. And you should understand the oxygen and carbon pi bond. For an example, you should understand this was carbon and this is oxygen. This was carbon and this is oxygen. So pi bond are like this. This is carbon and this is oxygen. So its pi bond are like this. You should understand, like this. And this carbon which we are talking about has got the sp2, has got a lone pair in sp2 hybridized orbital like this. So the pi bond of the C double bond O is like this and the lone pair is like this. So you should understand these 2 electron pairs, this pi bond and the lone pair, are not parallel. They are perpendicular. And for resonance to happen, I have told several times that the orbitals should remain parallel to each other. And this is not a situation of being parallel. This is perpendicular, and for that reason this minus charge is not in conjugation and will remain localized at that carbon. So that is how you should understand, and that is what we have I have written on in the slide. It is sp2 hybridized, not parallel to pi system, therefore no resonance stabilization. So in the option number B also you saw the minus charge was not in conjugation, and the option number G also we have seen the minus charge is not in conjugation. Now we are going to sum up all the features we have seen one by one from A to F. Now we are going to recapitulate it. We are now going to make a comparison to put a final hierarchy. Now first thing you should remember, carboxylic acid. This is a functional group which is by name you can understand has got high acidic power. Its name is carboxylic group. This is carboxylic acid group. So you should understand, and this is alkane, carbon, hydrogen. These are hydrocarbons. Hydrocarbons are less acidic as a category in comparison to carboxylic acid category. So from this important fact, you should keep the hydrogens belonging to carboxylic group as the priority. Then will come the hydrocarbon hydrogen. So on this ground, you understand D and F. As you understand D and F, this was hydrogen number F and this is the hydrogen number D. Both are associated with the carboxylic group, and as I have told, these are more acidic functional group than the hydrocarbons. Okay, and amongst D and F, I have illustrated, I have explained that this hydrogen, the F hydrogen, is engaged in the intramolecular hydrogen bonding, so it becomes difficult to get this out as H plus. On this basis, the D is more easily taken out, so it's more acidic in comparison to F. So I have written D more than F. And finally, A, B, C, E, G all belongs to hydrocarbon, carbon, hydrogen. Okay, then we have to categorize them accordingly. Now, amongst these, E is most acidic because I have already explained, once you take out this E, the minus charge comes, and you can revisit the slide where I was explaining the anion created by removal of E, that this ring as well as this ring both gets the aromatic character. So that aromaticity is the driving force. Okay, so E is coming in priority. Then will come A, B, C and G. Now amongst A, B, C and G, A is now at the top. Why? Because you have seen we had drawn 6 resonating structures. You can revisit the slide. For A anion, we had drawn 6 resonating structures. So there was an extensive delocalization, but aromaticity was not coming. But in the E, the aromatic behavior came. That is why E remains in the leading position. And since A had 6 resonating structures, C, you can revisit the slide, you will see 3 resonating structures, and B and G, as you know, the electrons remained localized, there was no resonance stabilization, so last B and G are coming. Now how to break the tie between B and G, you should understand. In the case of B, if you put a minus charge here, if you try to find the steric number, you understand with this carbon one more hydrogen remains there. So if you find the steric number 1 sigma, 2 sigma, 3 sigma, and this is a lone pair. So steric number is sum of the sigma bond and lone pair, you will find it as 4. So the hybridization will be sp3. However, if you are going to remove this hydrogen, the minus charge comes, and now here 1 sigma, 2 sigma, and this is a lone pair. So sum of sigma bonds plus lone pair 3, hybridization will be sp2. The sp2 has got higher s character. In sp2 the s character is 33 1/3%, whereas in sp3 the s character is 25%. And electronegativity is directly proportional to the s percentage. Higher the s percentage, higher will be the electronegativity. So the carbon which belongs to G is more electronegative, and if the minus charge remains on more electronegative, it suits it better in comparison to if the minus charge was on less electronegative, where the S character was less. On that ground you are able to decipher that G is a better option than B. So finally, putting all the bits together, you found that the first is D, then F, then E, then A, then C, G, and finally B. So we have taken all pain to dissect this question to a very basic, very fundamental level. I have made the anions one by one, then saw whether there was any possibility of delocalization, how many resonating structures were formed. Is there any possibility of aromatic character? If the delocalization was not possible, what about their S percentage? All those fundamentals I tried to keep in this problem. I hope you must have got the fundamental behind this problem, and similarly we are going to do a lot more problems in future also. Till then, take a good care of yourself and keep visiting my previous videos. You will get a lot after looking at all those problems. Thank you very much.